Right, let's get on with some quantum mechanics. We'll start with energy levels. One of Bohr's key discoveries was that atoms possess discrete energy levels. Their energies are said to be quantized. Unlike a gradually cooling object, an atom is characterized by a series of discrete energy levels, so it can't lose energy in a continuous manner. Instead, it jumps from one energy to another lower energy level, emitting a packet of electromagnetic radiation, i.e. a photon. It may continue this process until the ground state is reached. Each atom is a packet of EM radiation, with a frequency determined by the energy of the photon. If a photon jumps from energy state EJ to a lower energy state EI, then the emitted energy is that of the photon, E photon, and as a frequency of E photon, H multiplied by FJI, which is the frequency EJ minus EI, where H is the Planck's constant, often written in terms of the angular frequency, which is 2 pi f, and the energy of the photon is E photon, a H bar omega Ji, which H bar equals H over 2 pi, which is the Planck's constant, and each kind of atom has its own ground state. Now, with exponential decay, this is our first example of quantum indeterminism, and it was discovered by Ernest Rutherford in 1900. And one remarkable fact is that nuclei can be absolutely identical. This is impossible in the macroscopic world. I mean, imagine two snooker balls. No two snooker balls can ever be the same. There's always going to be some microscopic differences, or in their weight, shape, or etc. But all atomic nuclei of a specific kind in the ground state are absolutely identical. But although identical, they do not decay at identical times. There is no property telling a nucleus when to decay. Each nucleus of a specific kind, take uranium-238, has the same probability of decaying in the interval delta t. We write the probability as lambda delta t, where lambda is the decay constant of a given type of nucleus. This is statistical behavior. U-238 nuclei have a small decay constant but survive for billions of years. But an individual nucleus could decay in seconds, and a nucleus that's been around a long time is no more likely to decay in a given time than one just created, which is quite remarkable, if you ask me. But if at time t there are nt nuclei of a given kind, then in the small interval t to t plus delta t, the decrease in n is the number of nuclei that decay in a given interval. The average number of nuclei decaying in the given interval is equal to the number nt of nuclei that were present at the start, multiplied by the probability, lambda delta t, that any one of them will decay. Any one individually, any one of them will decay. So on average, the number of nuclei changes over the interval by delta n, which equals negative lambda n delta t, showing that n decreases as nuclei decay. Now, dividing by delta t and taking the limit of a small time interval gives dn over dt. Which is the differential, and now the time taken for half the nuclei to decay on average is the half-life, t 1/2. Taking nt to be n of 0, e to the minus lambda t, we have 1/2 equals e to the minus lambda t 1/2. So t 1/2 equals logarithm of 2 over lambda, or in this case 0.693 over lambda. Hence, this is our decay function, our exponential decay function, which is basically saying that the quantity keeps halving. It's the half-life of this. And that's it for this small lecture. Please do subscribe though, because there'll be plenty more coming.